Hello chemists, this is Ms. Placino, and in this video we're going to be talking about lab number 5, recycling aluminum. Before you really get into this video, you should watch the previous one, the procedural overview of this lab, walking you through what you'll actually do when you're running the experiment yourself. This video is going to talk about the pre-lab, so we're really going to focus on the concepts behind the chemistry you're performing and some of the calculations that you'll need to analyze the purity of your sample. All right, so let's dive right in. In the first pre-lab question, we are taking sentences written out in English and we're going to convert them into chemical equations. So question 1a, aluminum reacts with potassium hydroxide and water, yielding potassium aluminate and hydrogen gas. All right, so if you think back to the video about the procedure, this is really the first step where we take aluminum metal. And I'm going to leave like little blanks up in the front so I can balance and put my phases underneath the substance just so I have a little bit more room. Aluminum we're going to be using in the form of foil. You'll just rip it apart into smaller pieces. Hopefully get that reaction going faster. You're going to take potassium hydroxide, KOH. It gets dissolved in water, so that's going to end up being an aqueous solution. I'm going to let me write in that one specific spot. Try this again. There we go, that's better. And water, H2O. That will, of course, be a liquid. And as this reaction progresses, I will just have it in the hood heating up, and it's going to start to bubble. And we're going to be producing potassium aluminate, KAlOH4, and the bubbles that are produced are hydrogen gas, H2. And potassium aluminate is an aqueous substance. When this reaction takes place, it's going to turn kind of like a really dark brown, almost black color. We'll know the reaction is taking place because of the bubbling. That means that hydrogen gas is being produced and it is escaping. Since we're producing hydrogen gas, a flammable substance, it's really important that we run this reaction in the hood. That's going to allow the hydrogen gas to be removed from the room, just making it safer. After you have run this reaction, you're going to take that black sludgy mixture that you've created, that is really just the aqueous potassium aluminate, and you're going to gravity filter it. So that's the one where you've got your traditional filtration funnel, pour everything through, patiently wait, and collect your filtrate. From that black gunky solution, you're going to, if everything goes correctly, filter out a very clear completely transparent solution of potassium aluminate. From there, you're going to add sulfuric acid, H2SO4. That will also be aqueous. That's going to produce aluminum hydroxide, AlOH3. Water, H2O. And potassium sulfate, K2SO4. As soon as you mix the sulfuric acid in with potassium aluminate solution, you're going to form a white solid. That white solid is going to be your aluminum hydroxide. It is insoluble. Your water will remain as a liquid, and potassium sulfate is soluble in water, so it's going to be an aqueous ion, or aqueous ions, I should say, floating around in solution. You're going to take this mixture, you're going to get it on your hot plate, stir plate, get it heating up, and get it stirring. And the aluminum hydroxide that you've produced, that white solid, AlOH3, is going to continue reacting with the excess sulfuric acid, H2SO4, still aqueous, to produce aluminum sulfate, Al2SO43, and water. As this occurs and you're heating and stirring and you're continuing to get the white aluminum hydroxide to react with the sulfuric acid that's in solution, it should go completely clear again. That means that we are working, or I guess we've produced is a better way to describe it, aqueous aluminum sulfate. Okay, then we have the aluminum sulfate reacting with potassium sulfate and water to yield alum. potassium aluminum sulfate dodecahydrate. That's a mouthful, so you can definitely see why we just call it alum. So let's go ahead and finish up this equation. We're going to take our aluminum sulfate, Al2SO4 3. That's aqueous. It's going to react with the potassium sulfate, K2SO4, also aqueous, and water, liquid, to produce alum. So that is KAL. Oh, geez, that looks terrible. AlSO4 2. And dodeca is telling us 12 water molecules. And that's going to be aqueous when we first produce it. So just to kind of review, in step A, you're going to produce the potassium aluminate solution. That's going to be like that black gunky substance. You're going to filter it so that you've got just your potassium aluminate. You'll add sulfuric acid, which would cause a white precipitate to form immediately. That's aluminum hydroxide. As you heat and stir, the aluminum hydroxide will react with the excess sulfuric acid to produce aluminum sulfate. Aluminum sulfate is water soluble, so that solution will go clear. And you're just going to continue heating and stirring. And then overnight, really, letter D is going to take place, where the aluminum sulfate and the potassium sulfate that are in solution are going to react with water to produce alum. And hopefully, if everything goes well, when you get back to you come back to the lab the next day, you should have alum crystals. If not, don't panic. The alum is still in there. We'll talk about how to get it out. All right, so let's do a little bit of balancing. I'm going to walk through the first one with you just because it's kind of difficult to do. I'll give you a hint. We need to have 2 potassium aluminates formed. That makes it a little bit easier to figure out. With a coefficient of 2 in front of KAlOH4 in parentheses, that means we're going to need 2 aluminums and 2 potassium hydroxides. We also need a 6 in front of the water and a 3 in front of the H2 to get it balanced. The rest of them are fairly straightforward. That one's a little bit nasty. I guess these are a little nasty as well. I would suggest to pause the video and try to figure them out now. All right, so you can take a minute and check over your work. Oh, I just realized I got a couple of mistakes there. Let's do that. Sorry about that. Put this back in there. Okay, so just to quickly recap, for B, you should have 2, 1, 2, 2, 1. C, coefficients are 2, 3, 1, 6. And letter D, 1, 1, 24, 2. Okay, question 2, we're told to combine the reactions from question 1 to provide the overall reaction for the synthesis of alum. All right, in order to combine those reactions, basically what we want to do is look for substances that show up as a product in one equation and a reactant in another equation. If they're present in the same quantities, they will completely cancel each other out. For example, if you look at reactions A and B, potassium aluminate shows up on the product side and on the reactant side with a coefficient of 2. Those will completely cancel one another out. We can do the same thing with the aluminum hydroxides. Take a second, go through and see if you can cancel or simplify other substances. Hopefully you found aluminum sulfate, potassium sulfate. Now we've got a lot of simplification to do with water. So let's see, I've got 6 waters over here, 6 over there. We've got 2 waters here. It's going to give me 22 over there. And that really leaves us with our aluminums, our hydroxides, the hydrogen, H2SO4, water, and the alum itself. So if we're to try to write that whole reaction, I've got 2 aluminums plus 2 potassium hydroxide plus I can just combine the sulfuric acid, so in this case 4 H2SO4 aqueous plus 22 water, really big coefficient, yields 2. I'm just going to write alum because I'm going to run out of space. ALUM, that is that substance just above it, plus 3 H2 gas. Whew. So that is a lot of work to try to come up with that overall reaction. This is not something I'm going to expect you to do on the quiz. I do expect you to take the equations provided to you and balanced and be able to simplify down to something like this. But I will not expect you to take all the reactions and translate them into an equation. The whole reason that we go through that process of figuring out the overall equation is so that we can answer questions like number 3. Question 3 is a theoretical yield problem. So we're told if 1.02 grams of aluminum metal is used for the experiment, what is the theoretical yield of the reaction? Basically, how many grams of alum could be produced if all of the reactants became products? So in this case, and as well as when you're in the lab, aluminum is going to be our limiting reactant, meaning it's going to limit the amount of product produced. It's the substance that's going to run out first. Potassium hydroxide is present in excess. Sulfuric acid is present in excess. Water is present in excess. So there'll be plenty of those molecules floating around to react with, but eventually we'll run out of aluminum and the reaction will stop. So let's talk about how to calculate this. I've got 1.02 grams of aluminum. I'm just going to put that over 1. The first thing I should do anytime I'm solving a stoichiometry problem is try to get to the moles. In order to get out of grams of aluminum into moles of aluminum, I need to look up the molar mass of aluminum. For every 1 mole of aluminum I have, I should have 26.98 grams of aluminum. That's just something you can either Google or look up off the periodic table. I'm going to be specific and say moles of aluminum here. The whole reason we go through this process of trying to figure out the overall equation is so that we understand or we know the mole ratio between our products and our reactant. So we're interested in producing alum, and we know our limiting reactant is aluminum. Based on the balanced chemical equation, for every 2 moles of aluminum present, I should be able to produce 2 moles of alum. There's no way to know this ratio without going through question 1 and 2, kind of looking at all the individual reactions and combining them. Whether you want to write that as a 2-to-2 ratio or a 1-to-1 ratio doesn't really matter. And finally, we're asked for grams of alum. So for every mole of alum, it has a mass of 474.4 grams. But look what we've done here. We've taken grams of aluminum and cancel the grams to get to moles. Moles of aluminum can cancel to get to moles of alum. Moles of alum cancel to give us an answer in grams. All right, before we pull out calculators and start doing any calculations, let's just quickly think sig figs. How many significant figures can I have in this answer? Hopefully you're thinking 3 sig figs. The only measured value we have is the mass of aluminum. 1.02 grams have been used. The molar mass of both alum and aluminum are values that are not measured. They're just looked up. And you have an infinite number of sig figs for the coefficients in front of any substances in a balanced chemical equation. So I can only have 3 sig figs in my answer. If everything goes perfectly and every last atom of aluminum is turned into alum, I should be able to make 17.9 grams of alum. Okay. Again, that's theoretical yield. In theory, how much can I make? This is all just based on calculations. Question 4, you go into the lab, you run the reaction, and you're able to collect 6.55 grams of alum. What is the percent yield? Okay, we haven't had to calculate a percent yield before as we haven't run any synthesis reactions, but percent yield is really simple. Percent yield is equal to the actual value, what did I actually make and collect in the lab, divided by the theoretical value. In theory, if everything went perfectly, and things rarely do, how many grams of alum could I have made? And it's a percent, so of course we'll multiply by 100. Our actual value is 6.55 grams. So after running the reaction, collecting our alum crystals, letting them dry overnight, put them on the scale, you find they weigh 6.55 grams. We just calculated in the previous question that if everything went perfectly, we could have made 17.9 grams. It is not uncommon to have low-ish % yields. This is definitely not great by any stretch, but it happens, and it happens for a variety of reasons, which we can discuss later. (36.6% yield. Not great, but that's the reality of the situation. All right, moving forward. I think question 5 you can get through if you watch the video about the about using the vacuum filtration with the Buchner funnel, so I'm not going to review it again. But I do want to talk about question 6. This is a setup we're going to use to analyze the purity of the alum that you synthesize. So the first part of the lab is really making alum, going through the synthesis. The second part is trying to evaluate how clean, how pure is the stuff that I've made. So we're going to be using a really rudimentary setup to do this, basically a hot water bath to melt the alum crystals. A is a 3-prong clamp. We'll use that to hold on to the thermometer, which is letter B. Uh-oh. Oh no, there it goes. It's being very stubborn. Sorry, chemists. You've got your alum in a test tube, and the test tube is supported with a clothespin, letter C. This just kind of prevent your test tube, letter D, from bouncing around and being unstable. Just kind of keeps everything upright. E is going to be a 250 milliliter beaker. F is a ring stand, and G is your hot plate. So you'll take your alum crystals, it's kind of like this little pile of dots in there. You want to get the bulb of thermometer kind of like buried in there so that it's actually measuring the temperature of the crystals and not like of the air above it. You don't want to fill up that 250 milliliter beaker all the way with water. Not only is putting the test tube in there going to displace some of the water, but getting the water hot is the slowest part of this whole setup. If you fill it, it's going to take longer. And this is hopefully not the most exciting thing you'll be doing in lab for the rest of the semester, because watching water heat up is pretty boring. So I would say fill it up no more than half the way with water. As long as the sample itself, the alum, is below the water level, you probably got enough to operate. This setup is going to be used for determining melting point. Use just MP for melting point. We're going to test 2 different samples. First, we're going to test the reagent grade. So this is the professionally made alum. It's usually, if made in a lab, professional lab, it should be over 99.9% pure. You're going to test your synthesized alum. So the stuff that you have just made. And you need about ½ an inch of alum in your test tube. It doesn't really matter exactly how much you use. Melting point is an intrinsic property, so it doesn't matter if you use a tiny amount or a large amount, it's going to hit the same melting point temperature. But ½ an inch gives you like maybe the like the height of one of your fingers. Should be enough so that the bulb of the thermometer can be buried in the alum. Any more than that, you're just kind of going to take more time to get there. Much less than that, you might not have the bulb covered completely. You'll get some weird looking data. Okay. So really what's going to happen is you're going to take your sample, you're going to heat it up, you'll keep an eye on the sample itself, you're going to record the temperature when you first think you see the alum melting, and then you're going to record it again when you think it's completely melted. You'll repeat that for the reagent grade and the synthesized aluminum that you produced. You want to make sure that you're able to test both samples on the same day. Number one, that'll make sure you're using the same thermometer both times. The thermometers in the lab are not so great. You can definitely sometimes put it in some of the thermometers in boiling water and it'll tell you like it's 93 degrees Celsius. That's obviously incorrect. So by using the same thermometer, we cut down on equipment related discrepancies. Also, it's just really boring if I'm being honest with you, and you're going to want to get this over with in a day and not drag this out into 2. The reason we're able to use melting point as kind of a determination of the purity of the substance does have to do with the fact that it is an intrinsic property, and it should remain the same for all samples of alum. So on the next page, we've got this graph. We'll talk about the calculations. Hopefully you recognize this curve to the right. We should have seen this from my 10th grade chemistry. This is a heating curve. Okay, it's going to be kind of stubborn with the writing, so we'll just give it a minute. We know it's a heating curve because we see energy being added and the temperature is going up. So if we look at question 7a, which line segment represents melting? What's this line segment right here? Line segment BC. We have the solid phase, segment AB. CD is the liquid phase, so BC represents that transition from solid to liquid in our case, and if it's a cooling curve, from liquid to solid. Based on that heating curve, what happens to the temperature of the substance as it melts? Well, the line is flat, so that's telling us that the temperature remains constant. This is really kind of like a perfect heating curve. Ideally, once a substance starts to melt, it hits point B. It will not experience an increase in temperature until every molecule has gone from the solid phase to the liquid phase. That energy that we're adding is being used to compromise the intermolecular forces between molecules, not increase the temperature. So if the sample melts over a range of temperatures, you can conclude that it is not very pure. According to the literature, like if you were just to look it up, you see a melting point of alum between 92 and 93 degrees Celsius. It kind of depends, exactly which resource you're looking at, and as a hydrate, it might be tough to nail down an exact melting point. We talked about it a little bit in the previous page, the pieces of data that are recorded during the melting point test. It's your starting to melt temperature, and you're completely melted temperature. Ideally, if you have a really pure sample and your technique is correct, what should be true about your starting to melt and your completely melted temperatures? Yeah, they should be the same, because once the melting point is reached, temperature should not go up again until all of the crystals have left the solid phase and are now ready to be in the liquid phase. The formula that we use to calculate what's called percent difference, really just the difference in the melting points. We use the final or the completely melted temperature. Some of you are going to look at the substance as it's melting, and you're basically going to hallucinate that it is melting. Everybody does it. It's really difficult to gauge when it started to melt using this technique, but completely melted, it's a lot easier for people to see, oh, the solid is now completely a puddle, so it must have melted. So we're going to put completely melted. Actually, I'm going to change how I write that. You're going to take the final melting point of your synthesized minus the final melting point of the reagent grade divided by the final melting point reagent grade, again, the lab-made professional stuff, times 100. So the starting to melt temperature is not used for any of the calculations whatsoever. We'll use it to kind of evaluate purity in a different way. It's the final or the completely melted temperature, that over here, that's used to evaluate it, again, just because it's much easier to judge. So we'll take the final melting point of the stuff you made, minus the final melting point of the professionally made stuff, the one that we're extremely confident is 100% alum, divide by the final melting point of the reagent grade alum, and multiply that by 100. I'm going to leave you to do the calculation for question number 8 on your own. Prove to yourself that you can do, that you can apply that formula. All right, sorry this was a little bit of a long one. Hope you find it helpful, and we'll see you in lab.